Welcome to Future Forward, where we explore groundbreaking technologies shaping our world. Today, we're diving deep into quantum gravimetry, a field that's revolutionizing how we understand our planet. Imagine mapping Earth's gravitational field with unprecedented precision. That's the promise of quantum gravimetry, and it's poised to transform climate science, resource management, and our understanding of Earth's dynamic systems. This technology harnesses the strange and wonderful principles of quantum mechanics, and scientists are developing it for both space and ground or airborne missions. It's truly a new era for Earth observation. Let's look at space first. NASA is pioneering this frontier with its Quantum Gravity Gradiometer Pathfinder mission, or QGGPf. Slated for launch by the end of this decade, it'll be the first to test quantum sensing for measuring gravity from orbit. How does it work? The QGGPf uses two clouds of rubidium atoms, cooled to near absolute zero. At these extreme temperatures, atoms behave like waves. By measuring tiny differences in acceleration between these falling atom clouds, scientists can detect gravity anomalies with up to 10 times greater sensitivity than current methods. These anomalies reveal what's happening beneath the surface. Think underground water, mineral deposits, or even the subtle shifts from melting glaciers and tectonic motion. QGGPf isn't just about gathering data, it's a pathfinder designed to prove the technology for future missions. Plus, it's compact, about the size of a small microwave, and less prone to issues like drift that plague older instruments. Europe isn't far behind. The European Commission's Horizon Europe program is funding projects like CARIOQA, which stands for Cold Atom Rubidium Interferometer in Orbit for Quantum Accelerometry. CARIOQA aims to develop a quantum sensor for space, targeting a Pathfinder mission before 2030. They just kicked off their initial development phase in January 2024, focusing on the core quantum instrument. The goal here is European independence in this critical tech and, eventually, a constellation of satellites for continuous gravity monitoring. This will vastly improve how we observe changes in groundwater storage, ocean circulation, sea level rise, and ice sheets. So, what's the magic behind this? It often involves something called cold atom interferometry. Lasers cool atoms to near absolute zero, making their quantum properties shine. Then, the lasers are switched off, and the atoms fall freely due to gravity. By measuring the phase difference of these falling atoms, scientists get an absolute measurement of the gravitational field. This is a big step up from classical methods that can drift and need frequent calibration. It's not just about space missions, though. Quantum gravimetry is also being refined for use on the ground and in the air. Airborne campaigns, like those over Iceland and Greenland in 2023, have successfully used quantum gravimeters alongside traditional ones, proving they can provide absolute gravity measurements. These mobile units are fantastic for mapping gravity in tricky areas like mountains or coastlines. Ground-based quantum gravimeters are also popping up, helping monitor volcanoes, assess groundwater, and even in civil engineering for infrastructure checks. The ability to get high-resolution, reproducible measurements over time at specific spots is a game-changer. The data from all these quantum gravimetry efforts will wonderfully complement what we already get from satellites and on-the-ground measurements. An integrated approach means better monitoring of Earth's geophysical systems and improved models for climate change, water cycles, and geohazards. Of course, it's not all smooth sailing. The technology is incredibly complex. Operating at ultra-low temperatures and precisely controlling quantum states makes these instruments expensive and challenging to build and maintain. Sensitivity to external noise is another hurdle, but researchers are working hard to make these sensors more robust, compact, and effective. In a nutshell, quantum gravimetry is a revolutionary tool for watching our planet. With NASA's QGGPf and Europe's CARIOQA on the horizon, the next decade is set to bring huge breakthroughs. We're talking about a new level of understanding Earth's gravitational field, leading to smarter resource management and a clearer picture of the changes our world is facing. That's all for this episode of Future Forward. Join us next time as we explore another fascinating frontier of science and technology.